the scientific explanation for the southern grasshopper mice resistance to scorpion venom neurotoxins. The bark scorpion, also known as the Arizona bark scorpion, inhabits the deserts of southwestern United States. Scorpions have evolved to secrete pain-inducing venom to stop their prey from fleeing, as you see in this video of the scorpion stinging the spider. The southern grasshopper mice inhabit the same geographical area as the bark scorpion. They live in the deserts of southwestern United States and northern Mexico. Another species, known as the northern grasshopper mice, inhabits southern Canada and northern United States and shows similar neurotoxin resistance to scorpion stings. However, the research discussed in this video specifically focuses on the southern grasshopper mice resistance to toxic chemicals from the specific bark scorpion species. The scorpions are optimal prey for the southern grasshopper mice, and to evade the toxic scorpion sting, the grasshopper mice have evolved a special mechanism. As shown in this video of the grasshopper mice attacking the scorpion, the mouse shows no signs of pain-inducing venom. A scorpion sting injects venom that sends chemical toxins to specific areas of the body. These toxins can have many effects. If toxins from the venom reach specific areas in the muscle tissue, it can result in death due to paralysis of muscles. Temporary paralysis of an organism's arm or leg may not seem fatal, but paralysis of muscles used to breathe, like the diaphragm, is fatal and will most likely result in death of that organism. Scorpion venom can also interact with the peripheral nervous system, causing an organism to feel pain. The peripheral nervous system sends information to the brain about stimulus from the environment, causing an individual to feel certain sensations like pain. The scorpion injects venom that causes an organism to feel pain and most likely will result in death due to the inability of that organism to flee the scorpion predator. The grasshopper mice have evolved to evade both symptoms of the scorpion venom toxins. To understand this mechanism, we have to break down the central nervous system and its structure. The central nervous system is made up of billions of neurons, approximately 86 billion neurons. Along the border of each neuron, there are channels that function similarly to a door. The role of the channel is to allow particles like sodium or chloride into the cell to cause the inside to become more positively charged or negatively charged, depending on the ions that cross the border. The cell usually has more negative charges on the inside compared to the outside of the cell, causing a more negative charge on the inside. But if enough sodium ions cross the border into the cell, the inside of the cell will become more positively charged. If enough sodium ions cross into the cell will become alarmed. However, there must be enough sodium ions let into the cell to make the cell positively charged beyond its threshold in order to make it reach a potential to send a message to the neighboring neuron. Chemicals, like the toxins found in scorpion venom, interact with specific ion channels, causing them to change how opened or closed that channel or door is. If the chemical causes the ion channel to become more closed, ions will not be allowed to pass through the channel, preventing a message from being sent to the neighboring neurons. However, another chemical could cause the ion channel to become more open, making ions more readily available to pass through the channel, causing the cell to be alarmed and send a message. This mechanism allows the brain to receive information about environmental stimuli via a relay response of messages being sent from the neurons. Now that you understand how the nervous system functions, we can now study how the scorpion venom causes its prey to feel excruciating pain. Scorpion venom typically interacts with only one specific sodium channel in the peripheral nervous system. When the scorpion venom neurotoxin interacts with the channel, it causes it to become more open and allows more ions to flow through the channel. This causes the cell to become more positively charged on the inside. It is positively charged beyond its threshold and the cell becomes alerted. This neuron then sends messages to its neighboring neurons, which continue the relay response until the message rapidly reaches the brain and the central nervous system. This causes organisms like the spider to feel debilitating pain and unable to flee the scorpion predator. However, when stung by a bark scorpion, the grasshopper mice shows no effects of pain and acts as though nothing has happened. The toxins in the venom clearly have different effect on the grasshopper mice. When the bark scorpion stings the grasshopper mouse, the scorpion venom interacts with two specific sodium ion channels rather than just one. The chemical binds to the first ion channel, causing a similar effect seen before. It opens the ion channel and allows ions to readily pass through the gate into the inside of the cell. However, when it binds to the second ion channel, it blocks any flow of ions and essentially shuts the door so that ions cannot pass through the channel. Since one of the ion channels is blocked, there isn't enough sodium let into the cell for the threshold to be met. Therefore, no message is being sent between neurons to the brain. The brain receives no environmental stimulus of the toxin in the scorpion venom, and the mouse feels no pain. In the grasshopper mouse, the chemicals bind to the second ion channel because there is one different building block in its structure. This minor change in one specific ion channel in the grasshopper mouse allows them to evade the pain-inducing toxin injected during a scorpion sting.